like let's say I think most of you know that 1 plus 2 plus 3 plus so on plus n, right? So this is also called sigma n, right? So the sigma n series. So I think most of you know the proof as well. So let's call this S. So if we add another S, which is like n plus n minus 1 plus, I'm just writing that in reverse, plus so on plus 1, suppose plus 2 plus 1, right? So this is also equal to S, right? If we add them up, so this is 1 n plus 1, this is also n plus 1, right? And this is also n plus 1 and so on. So we will have exactly n times n plus 1 as the sum of this, right? So this is equal to 2s, right? If we add these two s's, so that implies s equal to n into n plus 1 by 2. So this is the basic I mean, this is I think covered in pretty much around class 9th or 10th standard. So, and another one is the sum of the geometric series, so which we kind of encounter in a lot of like algorithmic analysis, like when we want to find the complexities. So we encounter the following expression a lot of times, like which is like the series now is like 1 plus say r plus r square plus so on say r power n, right? So we can do we can formulate it pretty much the same way we did for that, like, but except like, so let me multiply the s with r, the same ratio. So this will be like equal to r plus r square plus so on plus r power n plus this ends with r power n plus 1, right? So again, if we sum this, so this is s into let's not sum this, actually let's subtract this, right? So let's subtract this, like s times r minus 1, right? If I subtract this from this, so you know that like all these terms will get cancelled out, so we end up having r power n plus 1 minus 1. So that implies s equal to r power n plus 1 minus 1 by r minus 1, right? So this is for the case when r greater than 1. Okay, so you can just take as a like homework or practice yourself for like what happens when r is less than 1. Of course, this kind of converges to 0, the higher term. So this can also be an infinite series. So but yeah, briefly, like, so 1 plus r square plus so on, in fact till infinity, is equal to 1 by 1 minus r. Okay, so so this we don't encounter in a lot of places while doing the complexity analysis, but this is an important equation in the like binomial theorem, or like in a lot of combinatorics actually. So this is one of the most fundamental thing for generating functions, like, so in case you have covered it in your part of GATE syllabus or during your graduate course, so generating functions is an effective, like, I mean, in fact, one of the most advanced techniques for computing the, actually estimating the enumerations. Okay, yeah, so let me know, like, I mean, so far if I'm rushing or like if it is too slow, so please do let me know. Okay, so yeah, I'm assuming no issues here. Okay, so let me continue with the next topic. Okay, so this is the sum, etc. And yeah, so let me also define, since we are at enumerations, so I'm writing in the next frame. Okay, so since we are talking about enumerations, so okay, before going to NCR, does anybody know like what is 1 plus 1 by 2 plus 1 by 3 plus 1 by 4 plus so on plus up to 1 by n approximates to when for a very large value of n? Can anybody? So you can type in the chat window. Okay, so I think this is this approximates to log n actually, right? So yeah, the proof is I think non-trivial, but yeah, even I remember by kind of memory. So okay, this is also like one of the useful equation that we encounter in while doing complexity analysis. Anyway, yeah, let's talk about NCR, N choose R, or the combinatorics, right? So NCR is one of the most powerful things in combinatorics. The definition is simple. I think most of you know that it is n factorial by r factorial into n minus r factorial, right? So of course, like I don't have to define factorial here, so everyone has, I'm sure, like are aware of factorial, right? So okay, anyway, so n factorial is equal to 1 into 2 into 3 into so on up to n, the product of n numbers. So by convention, 0 factorial is considered as 1. Okay. Yeah. So one of the interesting things about NCR is that it also works for negative numbers. So that is, let's say, you can also compute like minus 1c, 1 is equal to anyway minus 1, because so nc0 equal to 1 for any number for any n, and nc1 is equal to n for any n. Okay, so after that, so NCR can be written as like n into n minus 1, so n minus 1 into n minus 2, so on, up to like, let's say, n minus, oh sorry, so this is getting very small, I think. So let me write it a little bigger. Sorry for clearing this content, but yeah, so let me clear the whole thing, or okay, I'll move on to the next tab. Okay, so yeah, so yeah, in fact NCR, which is equal to n factorial by r factorial into n minus r factorial, right? So this is nothing but n factorial can be written as n into n minus 1 to n minus 2 into so on, n minus r plus 1 into n minus r into so on, so which is equivalent to n minus r factorial, right? So what I'm saying here is, for example, 10 factorial is equal to 10 into 9 into say 8 factorial, right? Or 10 into 9 into 8 into 7 into 6 factorial, right? And so on, correct? So that way we can write it this way, and divided by r factorial into n minus r factorial. Of course, like you can just cancel these two out. So you will have r terms here. So r terms here, and so you will have r terms here, 1 into 2 into 3, so on, up to r in the denominator as well, right? So this can be used actually to compute the negative values, like let's say, so what is minus 1c1 is minus 1, okay, and minus 1c2 is equal to minus 1 into n. So basically nc2 is nothing but n into n minus 1 by 2 factorial, so which is 2. And similarly nc3 is equal to n into n minus 1 into n minus 2 by 3 factorial. Okay, so let's also take nc4 is equal to n into n minus 1 into n minus 2 into n minus 3 by 4 factorial. So minus 1c2 becomes minus 1 into n minus 1 is minus 2 divided by 2 is equal to 1, right? Minus 1c3, right? So minus 1 into minus 2 into minus 3 divided by 3 factorial. So obviously this cancels out, and this leaves us minus 1. And minus 1c4, of course, now you can guess it, so this is 1. And so basically it alternates between 1 and minus 1, right? So this works for 1 by 1 minus q, for example. So 1 by 1 minus q is nothing but 1 minus q power minus 1, right? So I hope everyone knows the binomial theorem here, and that's where the NCR actually came from, right? So the binomial theorem says that a plus b power n is equal to nc naught. So basically this is a power 0 into b power n plus nc1 into a power 1 into b power n minus 1 plus nc2 into a square into b power n minus 2 plus so on, right? So and towards the n, so it will be ncn into a power n into b power 0, so which is 1. Okay, I'm just writing for the sake of completeness. So let me just round it off with a different pen. Okay, so if you apply the same to this, so this will be equal to minus 1c0 into 1 power 0 into minus q power, so this is n, right? So minus q power minus 1 plus minus 1c1 into, of course 1 power 1 will be same, so now we don't have to worry about it. So to minus q power minus 2, right? So oh sorry, someone has come in. So plus so on, but anyway, eventually, so this will actually for easier computation, let's take it like let's take the q ahead, so it's same basically. So minus 1c0, this can become like minus q power 0 plus minus 1c1 into q power minus q power 2 plus so on. Okay, so yeah, am I right? I think minus q power minus 1, right? Yeah. Wait, it actually gets minus 2. Anyway, so this turns out to be the one I have told you right earlier. So if you apply these 1 minus 1 alternatives, so it becomes like 1 plus q square plus so on. In fact, q power n, I think, but yeah. So in fact, sorry, it doesn't end, by the way. So because there is no end to it, since n is less than 0. Okay. So anyway, so this you can kind of as a take-home assignment. So in fact, the exact assignment is a programming one. So that's our assignment 1. So which I'm about to give you. So is assignment 1 today is to code a function. Okay, so that returns NCR. Okay, value of NCR. So this is a little tricky. So you need to, like, if you just try to compute this using n factorial by etc. So the n factorial actually like quickly exceeds the limit of integer or long for that matter in C or C++ pretty quickly. I think hardly some, you can only compute till 20, n equal to 20 or so, maybe, yeah, 20 actually. So beyond that you can't go. So NCR, so you need to do it like a little cleverly. So let me see like who can do that. So that is for integers. So 1, this should cover large enough with large integers. Let's say large integers wherever possible actually. So that is this should at least be able to compute, like let's say if I say 50C10, okay, but 50C10 this should cover, but of course like it may not be possible 50C25 because the final value will exceed the integer limit, I guess, with 50C25. So second, so this should also work for negative numbers. Okay, so you need to handle negative numbers to be handled. And third point is, in fact, NCR also works for fractions. So fractions are, let's say, I would call it floating point numbers. Like let's numbers, be it floats or doubles in C++. So, but yeah, this is optional, like because the precision kind of can bite you. But yeah, let's see. So at least try the first two. Okay. Yeah, this is about I think, yeah, what I thought is, yeah, this is about NCR. Any doubts so far? Anybody? So, can you write in full screen Jamboard and while explaining the okay, so the Jamboard looks small, so greater than 50 can we use define. Satyajit, I didn't quite understand your question. Could you please unmute and talk? Hello? Yeah. Hey. Hey, thanks. Right. Okay. No, no, no. So, okay, I will explain. So before that, like, let me try to fix this Jamboard stuff. So if it is Satya, since you have anyway unmuted, you are unmuted. So is this very small now, right now? So let me. So if I say 100%, so the problem is this is. Yeah, actually, that's right. Okay, so let me. Okay, but let me just fit the screen. Here, fit this 100%. So this is good enough, right? Okay, yeah, cool. Thank you. Yeah. So what I was saying here is, let me. Yeah. So I'm not asking to evaluate like 1 plus r plus so on, that thing. So what you need to give is, you need to return, like, let's say double NCR, for example. So in fact, you can even like write two functions here. Like, let's say, let's say one is like, let's say it would return int or like long for that matter. So long, I think it's called long in C++. So which is of 18. Which is of 64 bytes, so which can cover up to 10 power 18, I think 2 in 10 power 18 or something like, or almost 10 power 19 it can cover up to. So the integer value can go up to 10 power 19. So anyway, so long, so sorry, where is it? Yeah, so it's long. The function signature will be long, call it NCR, right? So which would take two arguments. One is int n and another is int r. Okay, so your return value is long. Okay, so for example, so if I call NCR of 25 comma 2, of course, so this should return how much? 25 into 24 by 2, so right, so which is 300, I think. So this should return 300. Okay, and if I call NCR, let's say some 10 power 12. Okay, of course I told integer, right? So integer cannot fit 10 power 12, so probably you need to take long n. Okay, so if I say 10 power 12 comma 1, right, so this should return 10 power 12 to me. And if I say NCR of 10 power 6 comma 3, this should return I can't count it, so 10 power 6 into whatever, 10 power 6 minus 1 by 6. Okay, so which is 3 factorial, right? So 10 power 6 into 10 power 6 minus 1 into 10 power 6 minus 2. Okay, so this is the expectation. So this kind of covers the first part. Okay, and then okay, R can be, oh okay, I think now I understood your question, Satyajit. So if you're talking about negative values, so for negative values R can be any large value, right? So but yeah, of course I can't give beyond like r to be like let's say that doesn't fit in the integral range. In fact, like you can consider up to 1 million. So of course, and this is not a like very formal coding competitive assignment that you need to come like I'm going to evaluate your logic against some inputs. I would just review the code. So you just send me send me the file over email, and then I'll just review the code and give the comments. Or better, like keep it in a Google Doc. Okay, so better keep it in a Google Doc, and I would review your code, and I can also leave some comments. So I think this is a good opportunity to start writing better code, and you can um, think like kind of industry standard, like how to code well, right? So I can also discuss some best practices there. Okay. So yeah, so whatever the code, like don't worry about you, if you are not able to do it so well, or like let's say if it only handles very basic integer, like let's say it doesn't handle large values, etc. So don't shy. So just finish the code and just make sure that it is running for whatever the input sets, and just post me. And please also mention in the comments like if it whatever the functionalities you are not able to complete, like let's say it cannot handle large numbers, or it cannot handle negative numbers, or it cannot handle floating point. Okay, so for floating point there are two ways. So if you're coding in C++, so there is something called method overloading or function overloading, right? So function overloading. So you can use that, and you can define another NCR with let's say which would return which would take double or float for that matter, double n, and the r should always be integer. Okay, int r. Okay, and this would return double. Okay, so this can be another signature. Don't worry, like I will towards the end of the class, like I would again discuss about this, like what exactly I meant. So this is the one signature, this is one signature, and this is another signature. Okay, Satyajit, did I answer your question? Okay. Okay, yeah, thank you. And feel free to post in the group, like if you have any questions, so don't hesitate, just post in the group. And if you think some people are like very hesitant to ask question in public, so don't hesitate to ping me in private, so you're always welcome. Okay, so yeah, thank you. Let's move on to the next topic. I think we have already passed half an hour, right? Okay. So yeah, let me introduce a fairly useful let's say series which is called, I think most of you know this, like the Taylor's series, right? So the concept of Taylor's series is like basically pretty much every function can be expressed as a polynomial. First of all, wait, why a function needs to be expressed in polynomial terms? So for example, coming to the computer science, so we knew that like let's say to compare complexity of let's say two functions. So to compare complexity of two functions, what did we do? The very fundamental thing we do is to compare degrees, right? So degrees only work, compare degrees. Degrees only work when they are polynomial, or when they are in that like infinite polynomial series, right? So not infinite, like so only for finite polynomials, right? So second thing is often, so it's very helpful in computer science to estimate functions like let's say e power x, right? So to estimate e power x, so the best way is 1 plus x by 1 factorial plus x squared by 2 factorial. So I think most of you know this, right? So like that, so just like e power x, so pretty much any function, well, there is a catch that it has to be differentiable at 0. But yeah, let's not get into that. So pretty much every function can be expressed as a polynomial. So the fundamental idea is, let's say the function f of x, we want to write it as a polynomial. So let's hypothetically assume that it can be written as like a naught plus a1x plus a2x squared plus a3x cubed plus so on, right? So plus a power n x power n plus so on. So basically there's no limit to this. So you can kind of so as the n grows larger, so you can better approximate. So yeah, I'll come back to this little later. So now, so what is the value of a0? So if I just keep x equal to 0, so what term will I get? Like only a0 on the right hand side, right? So everything else, like all these values, so will become 0, right? So a0 is f of 0, right? So how would I get a1, right? So if I differentiate fx, right, f of x, so f dash x is equal to, so when I differentiate, the a0 term vanishes, that becomes 0. So this will give me a1 plus 2a2x plus 3a3x square plus so on plus n into a power, it's not a power n, I'm sorry, it's a suffix n, like a n, not suffix, I think that's called whatever, I don't care. So a n x power n minus 1 plus so on, right? So that implies f dash of 0 is equal to a1, right? So similarly, if I want to get a2, so what I would do is I will make f double dash of 0. Actually, I will differentiate f dash x again. So which is double differentiation of f of x. So which would give me 2a2 plus 3 into 2 into a3x plus so on, right? So this means this would give me a2 is equal to f double dash of 0 by 2. Okay. For that matter, if you continue doing so, so you would get a3 is equal to f triple dash of 0 by 3 factorial and a4 is equal to f, let me call it f power 4 instead of 4 dashes, f4 0 by 4 factorial and so on. In fact, for nth term, an is equal to, it will be fn 0 by n factorial, right? Okay, so which means let me get to the next tab. So which means your f of x is equal to f of 0 plus x into f dash of 0, let me call it f1 of 0, plus x squared by 2 factorial into f square f2 of 0 plus, this is not f square, let me write like this, f2 of 0 plus x cubed by 3 factorial into f3 of 0 plus x power 4 by 4 factorial into f4 of 0 plus so on plus x power n by n factorial into f5, so fn of 0 plus so on. Okay, so let us try to do something with the e power x, right? So let's say if f of x equal to e power x and try to get this. Let me know, like feel free to let me know through the comments that if this is a trivial one or like you have already gone through this in your undergraduate course, so we can skip it, but yeah, so let me quickly cover it otherwise. So okay, 1 2 3, okay, so I'm covering it. So simply, I think most of you know that no matter how many times you differentiate e power x, so you end up getting e power x, right? So well, the intuition behind e power x is little awesome thing in mathematics, so I think it's worth discussing that. So what is e? So it is exponent, right? So natural exponent. So why is it called natural exponent? So let's say you invested your money, or like let's say you lend your money to someone. Okay, you lent your money to someone who, like at the rate of, like let's say they will double it after 4 years, let's say, or like they'll double it, like they'll return the you gave them x, and they will give you 2x after like 1 year, right? So that is, so the rate of interest is 100% for 1 year, right? So that means the interest formulas, right? Like obviously, so your money is getting 1 plus 1 times in 1 year, right? So you turned little greedy and you thought, so what about like if I let's say take the interest in first 6 months. Okay, some latecomer here. Okay, yeah, so you thought that like, let me actually lend the money for 6 months, okay, and then take the interest back and again lend it, right? So that way, so you would get interest of interest, right? So that means, but however, of course, you can't charge the 100% for 6 months, right? If it is 6 months, of course, you will get 50% of the interest, right? So that is in your first, whatever the money you have x, so after first 6 months, you will get 1 plus 1 by 2, right? So your money will become 1.5x, right? Then this whole amount will become another 1.5 times in the next 6 months, right? So which is 1 plus 1 by 2 power 2, correct? So then you realize actually this is better. So obviously value of this is 1.5 whole square, so which is 2.25, right? So that means by charging, like, let's say by collecting the interest after 6 months, by splitting your lending period into 6 months instead of 1 year, so you got this 0.25 times extra, so which is equivalent to what, 12.5% additional, right? So you would have otherwise gotten only 2x of money, and now you are getting 2.25x of money, correct? So now let's say you became even more greedy, right? So that means you now want to collect your interest like for every month, for that matter. So what happens is your interest will become like 1 by 12, right? But that is multiplied by 12 times. Sorry, that is exponentiated by 12 times, right? Because so the simple interest calculation, or like the cyclic interest calculation, right? So now this has become 1 plus 1 by 12 per 12. So theoretically, if you keep going like this, right? So how much can you charge? Like how much will you get? Like so what is 1 plus 12 power 12? Let's say, let me think. So 1 plus 1 by 12, okay, and power 12. Okay. So this is 2.6 times, right? So which means 30% more than 30% more than what you would have gotten otherwise. Like, I mean, if you haven't collected for the whole year, right? If you just collect it every year, right? So which is awesome. 30% more is, of course, like everyone likes it, right? So if you further becomes greedy, right, and probably you want to charge like interest every day instead of even monthly, right? How much will it become? So let's take it as like 1 by 365. Let's consider it as 365 days, and then let's call it 365, right? So what is this value? What will this become? Right? So okay, let me simply replace this here. So paset. So this is 2.71, right? In fact, if you further grow, like, so even like you may charge it hourly, of course, which is impractical. So if you go like, no matter how like smallest fraction you go, so basically this 1 plus 1 by n power n actually, so is equal to e. Actually this tends to e basically. So that means limit n tends to infinity. So this is the formal definition. I'm sorry, I'm writing here. So limit n tends to infinity, 1 plus 1 by n power n is actually equal to e. Okay, so you can try at your, like, I mean, you can try at home. Like, I mean, even miscellaneous ways to come up with value e and the various intuitive explanations for e, but e is an amazing number actually. And do you know what e stands for? Anybody? Quickly, without googling. 1, 2, 3. Okay, so e is like, I mean, since Euler has found it, like actually Leonardo Euler, so he, I think, termed it as e. So while doing, so e power x is equal to, let's say if we want to come up with the polynomial approximation for this, so we already saw that this is f0 plus x f dash of 0 plus so on plus x power n fn of 0 by n factorial plus so on, right? So that means f of 0, which is e power 0, is 1, right, plus x, okay, into f dash of x is e power x only, right? So if you differentiate e power x, so you will get the same value, right? So I hope everyone knows this, so why that is holding. So, well, there are other proofs, but the simple one we do it through calculus, through differentiation, is that let's call it e power x equal to y. So that implies x, if you just apply log on both sides, x becomes log y, right? So if you differentiate on both sides, so 1 equal to 1 by y into dy by dx. So that implies dy by dx is equal to y, which is e power x itself, right? So that is no matter how many times you differentiate it, so it just stays as e power x. So 1 plus x, and this is e power x, and if you substitute 0 for x, so you will get 1 again. So it will be 1 plus x squared by 2 factorial plus x cubed by 3 factorial plus so on. This is what you will get. Okay, so yeah, that's homework now for you. So similarly, find the expansions for, so consider it as assignment 2. Okay, I know I'm asking a little too much, but yeah, this would help you. So like, get the expansions for sin x and cos x, okay, and also try to let's say prove that e power I pi plus 1 is equal to 0. Okay, so this has a very this is like, I mean, this is one of the most beautiful expressions or equations in math. So this is also called mathematical beauty. So if you Google with mathematical beauty, so you would, in fact, Leonardo Euler, so Euler himself has found this relation. So e power I pi plus 1 equal to 0. So I is the the complex number I, right? So the beauty of this equation is, they say, like, the 1 is the multiplicative identity, right? So if you multiply anything with I, so you would say, if you multiply anything with 1, you will get the same number. 0 is the additive identity, and E is the natural logs kind of identity. It's the most basic element in the natural logarithms, and I is the basic element in the complex numbers, complex systems, and pi is one of the most fundamental magic value in geometry, right? So a relationship between these three is like involving these five is amazing. Okay, so you can prove that. That's your second assignment. So this is not a coding assignment. Anyway, so let's talk about enumerations. Okay, so enumerations. Okay, so enumerations means like assigning kind of numbers, like numerating, like, so assigning numbers to some set of objects, you can say that. So for example, like, so let's say, like, kind of mapping, you can say, like, let's say, so that, like, the number of how many ways you can permute, let's say ABC, right? So there are six ways, that, so n factorial for n objects, but like, how do you list them without missing anything? So we want to establish an orderly way to list them, right? So which is like like, for this we can follow the dictionary kind of style. So what comes next in the dictionary? So this ABC. So you try to change the minimal positioning from the right to left. So that is here. for ABC, so the next one comes as ACB, right? And now you can't still keep A in this position, so because there are no more combinations if you have A here, right? So obviously you have to change, and you want to change it with the next character to A, so which is B. So now you started with B, right? So and then you have the remaining in order, so which is A and C, right? And this is your next number. So then you still try to keep B, and of course you can keep it, and then you still can't keep A because there are no more such orders, unique orders. So you have to change it with the next available value, which is C, okay? And then the only thing remaining is A, of course. So this is your next lexicographic word, okay? And then you still can't have B because with B, so there were only two possibilities, AC and CA, which were already counted, so which were already covered. So you would go with C, of course, and then you need the other ones in order, so which is CAB. That is your next permutation. So now, of course, you can still keep C in the first position, and you can exchange AB, so which is CBA, and hey, sorry, Arvind has just pinged. Oh no. So a friend of mine is not part of this, and she's. I'm sorry. Yeah, there are two groups, unfortunately. So I think some people are not part of this. I didn't see that. My bad. Anyway, CAB, CBA, and of course there are no more possibilities. So we covered 6. So similarly, you can try for ABCD. So to generate the 24 combinations, right? So which I'm not going to do here, of course. So the point here is to not miss anything. So because we come across such enumerations in a lot of places in data structures and algorithms, and in fact in a lot of places in computer science. Like so that's why I would recommend enumerations to start with. Okay. Now, so let's say say combination, right? So this is permutation. So for a combination, so how would you do? So let's say you have say 3 zeros and 3 ones, for example, right? And this is the minimal number for 3 zeros and 3 ones in this sequence, right? So do you know how many total permutations exist here? So it will be 6 factorial by how much? 3 factorial into 3 factorial, 63. So which is 3 factorial into 3 factorial. So 6 into 4 into 5. So anyway, this will be 20, right? So anyway, okay. So since 20 is little long, so let's not list it. So let me take 0, 0, 1, 1, which is equal to 4C2. So there will be 6 combinations with 2 zeros and 2 ones. So what is the next number we can have in this sequence? So we can start with 0 still, of course. If we start with 0, so you can't exchange 1 and 1 because they are same. So there's no other way. So you have to go with 1. Okay. And then you sort the next things in this order, 0, 1. Okay. So you keep the next one. So this is the first, this is the second. Okay. So then the third one would be, so you can keep 0 here, you can still keep 1 here, and sort this 0 and 1. Okay. So which is 0, 1, 1, 0 is the next number. Okay. And similarly, the fourth one is, so you can't now keep 0 and 1 in the first place because so 0, 1 and 1, 0 on the right hand side are already covered. So now 0 can't stay here. So it has to start with 1. And let's take the remaining in order, which is 0, 0, 1. Okay. And then you swap the last two. So 1, 0, 1, 0 that becomes. And then finally, so it will be 1, 1, 0, 0 is your last number. Right. So yeah. So we got 6 combinations, right? yeah, if you have like, I mean, I know, like, I mean, I just kind of rushed through the details, but yeah, you need little practice for this. So, and this is very important. Next one. So let's say there are just two symbols, say A comma B. Okay, so how many two length let's say how many two length words can you make? Okay, so obviously it's 2 square, so how can you enumerate them? So like how can you how can you make sure that nothing is missed? Or let's go with 3 length words, so which should be 2 cube, which will be 8, right? So can anybody quickly list these 8 in the chat? Like, it starts with triple A, of course, and ends in triple B. Okay. Yeah. Oh, Satyajit, thanks. You meant, I think 63 is 20. Yeah. Somehow I'm not getting any ping or like any sound from this one. Oh, I think, is it because I have turned off the notifications or muted it? I don't know. Okay. I don't know. 1, 2, 3, 4, 5. So triple A, A, B, A, B, A, B, B, and then B, A, B, A, B, 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 A, B. Yeah, exactly. Perfect. Thank you. So basically, I think you got the idea, most of you. So like, okay, we'll start with triple A. Sorry, let me go to this. So you'll start with triple A, and then so you will try to replace the minimal thing. So that way you will come from the right side. So the AAB is the next word. So then it cannot be AAB anymore. So I will go with AB. So then goes A. So this is the next minimal number, and then ABB. Okay. So since these two terms have already become BB, so of course, so you have to convert the first A into B, and then again you start with minimal BAA, so followed by BAB, BBA, and finally BBB, right? So 4 plus 3 plus 1, so 8, right? So if you see, so this is the binary system, right? So this is a binary system. So if you replace A and B with zeros and ones, right? If you replace A and B with zeros and ones, and of course that is your binary number system, right? Similarly, if you have 10 symbols, like which are, let's say 0, 1, 2, 3, so on up to 9, right? So this way you will get your decimal system. So decimal system is also actually follows the enumeration order exactly, because let me clear this off. Okay, so because if you take some, let's say just 2 length words, right, in your, let's say with the symbols 0 to 9, so of course since there are 10 symbols, so there would be 100 2 length words, right? I don't call it numbers because I'm not considering any weight to them for now. So obviously this will start with 0, 0, 0, and then 0, 1 due to the minimal replacement logic, right? So the minimal incremental logic. So 0, 1, 0, 2, so on, 0, 9. So once you can no more have 0 in the first place, of course. So now you have to start with 1, and then again I will start with the minimal minimal element on the right side. So 1, 0, 1, 1, so on, 1, 9. So of course now I can't have 1, I cannot have 1 anymore, so it will be 2, 0, so on, 2, 9, and so on. I'll go to 9, 0 and 9, 9, of course, and this is the end of my 2-digit numbers, 2-digit words, 2 length words, right? And this is our number system, end of the day, right? Okay, that's all I wanted to say. And here is an assignment, assignment 3. So, which is, let's say, given an alphabet, okay? So, given an alphabet, so alphabet, it's called sigma, right? So, sigma is equal to, say, whatever, some numbers, 1, 2, 3, so on, n. So, these are the symbols. Don't treat them as digits. So, these are the symbols given an alphabet, sigma, okay? And So and a rank R, or and a rank R, yeah, and a rank R. So you need to find so this is a coding assignment, by the way. So return, so the, let's say it's not the word, but return the array of symbols, so which is, let's say it's an integer array, so return the array of elements, return the array of elements which is the permutation of that rank, which is the, I will define what is rank, I will define what the rank is, which is the permutation of that rank. Okay, so what I mean to say here is the last one is question mark. I wrote it so badly. Okay, so rank means, like, let's say coming to the case of AAA to BBB, right? So which was 2 length words. So I would say with n length, okay, and sorry, which yeah, I would say given n, you need to consider like as an n length. So that means your rank 1 so would be, so okay, my input is only n instead of this 1 to n. Okay, so rank 1 would be 1 1 1 so on, n ones. Okay, rank 2 would be 1 1 1 so on, 2. Okay, in fact, let's take a small like even smaller example. Like, let's say I would give n equal to 4 and say rank equal to 5, suppose. Okay, so that means it starts with 4 ones, right? Then 1 1 1 2 1 1 3 1 1 4 and then 1 1, there is no 1 1 5, right? So 1 1 2 1 it will be. So the next sequence would be 1 1 2 1, right? So this is the 5th rank, so its rank is 5. Okay, so let's say let's say for n equal to 4, how many numbers can be formed? Let's say with of say length 4, so it would be 4 power 4. Okay, because you have 4 slots and so you have 4 options to fill. So that means for n, so there will be n power n total numbers. Okay, so and of course the code, like I mean the complexity is very high, but so you can't do this by just listing those numbers. So you need to think little smartly, because when we replaced this third positions 1, right? When we replace this third positions 1 with 2, so why did we have to replace? Because we have covered some x numbers, right? And what is that x? So what is the significance of it, right? So yeah, that's what you need to understand. So you just work out through some examples, you should do it, you should be able to do it. Okay, let me give you the signature of the function. So let me just clear this. Okay, oh wow, it's erasing it so late. Okay, so the signature is the signature of the signature that you need to implement is let's say it is the integer array. I don't know the C syntax. It, I think, gives the integer pointer, I think, to the array. But yeah, please check your syntax. Integer array, this needs to return, and let's call it permutation, okay, for a given rank. So you would be given int n and int r. Okay, so that is your function. Okay, so this is part 1 of this assignment. So next part is, so given a permutation, you need to return the rank, and this is actually easy. So which means your signature will be int say rank. You need to give for, let's say, an integer array of permutation and length n uh, I know this looks daunting, but if you just work out through some examples. Okay, for the second one I can give an example. Like let's say I would give the sequence like the array of integers, like let's say 1 3 2 5 or 1 3 2 for example, and for 1 3 2 as the array to the function call, and n equal to say n equal to 3 because there are just 1 2 3 the numbers. So I think n is the redundant value here, because by looking at, oh, in C you can't know the size of the array, right? So okay, the n will work as the size of the array, and let's say r equal to say oh sorry, the r won't be given. I'm really sorry, so I'm being stupid these days. So okay, so the r won't be the part of the signature. Okay, so you need to find the rank of this. So that's what you need to return, the r value. Okay, so what I mean to say here is, I hope this is visible. So if not, okay, let me write it here. So 1 2 3 is of rank 1. Oh, actually this is right next value. So 1 3 2 is of rank 2. So you need to return 2 for this case, for the example I had taken here. Okay, so yeah, let me know if this is not clear, so we can anyway discuss in the group. Okay, with that I will stop enumerations. Yeah, any doubts? Or what is 405 total, Satyajit? Oh, okay. Never mind, thank you. Yeah, so let's start with expression trees. So this is where your kind of actual data structures class or the concepts start. Okay, I thought I would cover complexity theory, but complexity we can come again after discussing some algorithms, like at least some sorting algorithms. Okay, so let me start the expression trees. So okay, so for a machine, I think I have already told you, so everything is an expression to a machine, right? Let's say when you say a equal to b plus c, so in fact how many operands are there in this expression, and how many operators are there? So you know the operators and operands, right? Operators and operands, right? So how many operators are there and how many operands are there? Quickly, through chat, someone. 3 operands, good. 2 operators, of course, right? So plus and equal to are the operators, right? So we don't consider equal to as an operator in general. So what happens is, for a machine, so let's say simple b plus c is an expression, right? And a equal to whatever some k is another expression. Okay, so we have someone knocking. Okay. So for a equal to b plus c, so how that is evaluated by a computer is, like let's say it takes, so it first constructs the tree for b plus c, okay, and then says equal to, and it has this a equal to b plus c. So this is the construction for the tree. So equal to is at the root and a is here. So and then on the other side, so you know that like these are intermediate nodes, okay, and this is the root node. So this is the root, okay, these are the intermediate nodes, and so this is the children. So child, this is child 2 plus, and b is child 2 plus again. So and similarly plus is child 2 equal, and where equal symbol is the root of this tree, right? And a, b, c are also called leaves, right? The plural of leaves. So yeah, so if you know, if you notice, of course, like all the operators actually remain as nodes. Operators are nodes, and operands will be leaves. I'm sorry, everything is a node. Operators are intermediate nodes. Pardon. So intermediate nodes. Okay. So of course this is as simple as it can be. And now let's try to uh, go through the traversal techniques, right, or evaluation. In fact, the notations. So this is what I wanted to discuss today. So notations. Of course, I think most of you know there are three famous notations, right? So prefix, postfix, and infix, right? In fact, people talk in this order: prefix first, infix second, and postfix. Okay, so yeah, let's discuss these quickly. So you know that prefix means, so left and right, so will be like in this order always, like in all these three traversal techniques. So for prefix, you would visit the node as like first node, and then for postfix, let's say left and right stay as is, and you would visit node as the last, right? And then for infix, you would visit left and right as is in that order, and you would visit node in the middle. So what that means, so we will explore. So node here, so node in the last and node in the beginning, right? So yeah, so what that means is recursively, so it's like you start with root, right? So you start with root, and let's call prefix first. Okay, so let's go with prefix. I'm just wondering, like, if I should give few more practices for expression trees, or okay, so let's go with some more practice for expression trees. Let's see if we have time, so we'll cover the other the traversals. Okay, let me think. Yeah, so because we need a lot of practice for these notations, so let's just give more examples for expression trees. Okay, so I'm sorry, so why is this locked? What's happening to this? Okay, sorry for that. Yeah, so let's talk about few more expression trees, right? So expression trees further, right? So let's try to have a like expression tree for a star b plus c, right? So obviously, so we need something for b plus c first. So there are two operands here and three operators, right? So you'll have star a plus b and c, right? So this is as simple as that. So now I will throw questions to you. So you need to give me the depth of the expression tree. Okay, depth of the tree. So what is the depth of this tree? So depth is like, let's call it like 0 or 1, people call it 1. So this is second level, level 2, and this is at level 3, right? So depth of this tree is 3, I would call it, right? Actually, different authors have different notations. Someone starts with 0, someone with whatever. So some people mention levels, like, so they start with 0, they call this as level 0, level 1, level 2, and some say from the like bottom up. So it doesn't matter actually, end of the day. So anyway, at level 1 or 0, so we have star, and we have at next level we have a and plus, and the bottom level, so we have b and c, right? So there are 3 levels, and so depth is 3. 3 is the depth, right? So let's take like a plus b star c plus d. What is the depth of it? A plus b star c plus d. Anybody? So obviously this will be star plus a b plus a b. Okay. Not 4. I think it's 3. Lasani. So it's star plus plus on either side, right? So star plus plus on either side. So A, B, sorry, this is C and D, right? So it is 3. Convinced everyone? Okay. So now another one. So let's have the expression is A plus B star C by D minus E. Quickly. Height, or someone also calls height of the tree. So what is the height of this A plus B star C by D minus E? Sorry, if you A plus B star C by D minus E. Three. I don't know. So let's take plus A. So I would say star. Maybe minus comes here. E. Star would be like probably B, and slash C D, right? So yeah, but it goes from right to left, right? So B star C happens first, I think. So B star C it would be, and then slash here, then D, okay, and minus can be here. So 1, 2, 3, 4, right? Am I missing something here? So let me make it a little clear, or like let me just undo these. Okay, A plus B star C, right? Like, so star will be here, so it would be B, okay, and C. So okay, I got it. I think we should rather do, instead of star, A plus slash. So let me do the B star C first, okay, and divided by D, and this whole thing has to be removed from E. So even the best case 1, 2, 3, 4, 5. I think we, so 1, 2, 3, 4. I think, yeah, I'm getting 5 levels. Precedence and associate, exactly. We can talk about that, exactly. So the precedence and associativity matters, but however, in general, the precedence is, at least today itself I checked accidentally. So the star and this slash, right? So they happen from left to right. So because B star C happens first, slash D. At least I checked on Java compiler, but I'm not sure if that is a standard. So that's like homework for you. So you can decide like how that works. Okay. But even though with and for precedence, okay, between star and slash, I don't exactly know either. So you need to check it out. Okay. But either way, so this is just for practice. So anyway, so let me just move on to the next example. So same one. So you need to give the depth of the tree. So it is A plus log of B minus C. So can you tell me how many operators are here and how many operands are there? A plus log of B minus C. Three operands, awesome. So what are those three operands? Of course, operands are obvious, right? And how many operators? Okay, like we can go KBC, and someone says 2 operations or operators for that matter. So someone says 2. So what is the depth of the tree? Operators 3, operands 2. Okay. Operands are 3 obviously, right? A, B and C. So what are the 3 operators? Both are 3. Okay. What are the 3 operators? Yes. Yeah, this is what I wanted. So log is also an operator here, right? So except this is a unary operator. So right. So after all, what is an operator? So something that defines some operation, right? So the plus is defining addition, minus is defining subtraction, which we are very intuitive to us. And for a computer, it doesn't matter whether it is plus, it is minus, it is plus plus, it is minus minus, it is log, it is some function, it is some main, it is whatever it is. So everything is an expression, and like it just sees as some applying operators on them. Okay, and we just define those operations for the non-standard ones like logs, etc., log function main, etc., and just a machine simply just applies those operations, right? So here for a plus log of b minus c, now the expression tree, everyone knows that plus a. So now here comes some magic, which is log minus b and c. What's the depth? 1, 2, 3, 4. Okay, so why did I write log this way? Like, so plus is a binary operator, right? So plus is a binary operator. That's why it has binary operator, means something that can be applied on two operands, right? And log is the unary operator here, as I already told you, right? Clear for everybody? So that's why. So there is only one child to log. Okay. So we are so much used to the binary trees, and now the unary tree probably looks a little confusing. Okay. So, but is that clear to everyone? Okay. So now I would give you another expression. Okay, which. Okay. So for which you need to tell me the depth. Okay. So which is log of sine of x plus y plus plus. I hope everyone knows about y plus plus. It's the post increment operator. So the plus plus, right? What is the depth of this tree? Log of sine of x plus y plus plus. So how many operators are there and operands are there? Just कृपया बताइए. Operators for 1, 2, 3, 4, right? Right. Depth, please. Yeah, depth is 5. Everybody got it? So, yeah, this is the tree in case you want. So it is log of sine of, so then it has a like addition operator plus, so which is applied on x and y plus plus. So again, the plus plus is another operator which is a unary operator, so hence it has just one child which is y. Okay, so the depth is 5. Hope that is clear to everyone, right? So another one, next I would go with which is let me think through it. Actually, did I write anywhere? So I'm a bad teacher. Like I taught multiple classes of data structures and algorithms in India, and my notebook is too bad actually. I wrote it so cryptic that I'm not understanding it myself after 3 years. Anyway, so let me take this. Everybody's ready, I hope. It's f of g of x plus h of y, okay, and plus h of theta of 1. f of g of x plus h of y plus h of theta of 1. So how many operators are there? I know some operators are repeating, but yeah, you can count them, like, so they're not distinguishable because there are two pluses at least, right? So how many operators are there? Depth phi, is it like latest? No, it's old one. F of g of x plus h of y of x plus h of y plus h of theta of 1, right? Okay, I'm drawing the tree here. There will be plans. Depth 6, good. Let me check. X either h either y plus theta. Acha, so 1 2 3 4 5 6. Yeah, I too got 6. Two operators, eta key. Itna kam? No way, right? So let's see this. So yeah, let me take a different color to. So yeah, so this is the operator, right? So actually every intermediate node is an operator, right? We talked about it, like H, F, T. What is an intermediate node? So which is not a leaf, right? So F, G plus H, right? Kitne? 1 2 3 4 5 6 7, I think, right? So there are 7 operators. 8 operators, I don't know, like I think I got only 7. Okay, anyway, doesn't matter. Okay, I hope you got the idea by now. Okay, so one last problem, please don't be bored, stay patient. So one last problem is, let me call it, actually not last problem, so we need several of such things. F of x y z plus g of h of y comma x comma, say g of x, suppose, I guess. Yep, that's it. This is the trick. F of x y z plus g of h comma y comma x comma g of x. I think by now you can just look at the expression and see, try to get the depth. Can you not try to make a tree here? So you should get the tree in your brain now. At least I hope I can do that, but yeah, for me it's okay. Like so I can't do much in brain without writing. So anyway, so plus is the top level, obviously. Then comes F on the left side and it just dies there with 3 kids. So that's it. So we need to go to right. So plus G, H plus G, H, and Y and X are just another operands, and hence G of X. So plus G, H, G. I think 4. Right? Panch will. Chala, let's see. So let me take a different color just for fun. Okay. So plus, okay, F of x comma y comma z, okay, and G and H. So H has y comma x comma G of x. So 1 2 3 4 5. Oh, sorry, 5, right? So I just left the leaves. So yeah, I only counted the operands. So the depth is 5. That's right. Okay. So one last problem. Okay, and this is truly last. Okay. Let me have a new tab open. And this is white background. One last problem, which is okay, I would make it a little tricky. So hey, let me tell you, like, I mean, if you want me to stop, because someone told 2 hours is too long last time, so it's almost like we are approaching 2 hours. So please feel free to let me know. And I think most of the others are also feeling the same, so don't hesitate to say stop. Okay. So anyway, this is the last problem in this section. So let me call it this way. Like, let's say main of sub of add of phi, okay, comma some free of, say, pointer, okay, pointer. Okay, I think this is good enough. Like, can you read this and make it? I think it's pretty same and trivial. How many operators are there? How many operators are there? Wow, someone is coming almost towards the end of the class. So Aman, वैसे भी attendance तो नहीं है, so don't feel obliged to attend. So, okay. This one is also, like, I mean, simple. Let me just draw it. Like, so it's main. I hope it's visible. Or okay, let me go to the other one. It's main sub add phi, right? So, and then free of PDR. So main, and my main is binary function. Like, I mean, in fact, it takes 2 operands. So sub and sub takes 1. So add also takes 1. So phi and free of pointer. Okay. Where is it? It's here, right? This is the tree. So here main, sub, free, add. So these are the nodes, and add actually is a like unary node, which is counterintuitive, I know. And sub is also unary node. Sub add phi, and free is also unary, and main is the binary. That's why it has 2 children. Okay. That's it for expression trees. I hope you understood the point here. So for depth, yeah, and 2 operands. Of course, phi and pointer are the only operands. That's right. Okay. Thank you. Next, let's quickly see the evaluations. Notations. Right. We talked about, like, let's take A plus B star C, suppose. Right. So this is the expression tree for that. Right. So let's take the prefix notations, prefix, infix, and postfix notations, right? So prefix, infix, and postfix. So I think many of you know this. So again, as I told you, left, right, and node comes first because it's prefix. Infix, left, right, and node comes in the middle. And postfix, left, right, and node comes in the right. So what this means is, like, for this particular tree plus A star BC, what happens is, so I will start with root. So in fact, the code is something like this. It's as simple as this. Like, let's take a print. So what happens is, like, let's say prefix is nothing but prefix of tree. So which you generally pass root to it. Okay, is nothing but, since it is prefix, you directly print or visit the data at root. So let's call it root.data. Okay. Don't worry about syntax, like just ignore it. So print root of data. Then you recursively call the left first, so prefix of root dot left. Okay, and then you call prefix of root dot right, and that's it. Right, and this happens recursively. So I think we have discuss the recursive functions, tracing quickly in the last section, right? So in this section, we'll try to, cover that again in depth. So, yeah. but by the way, so since we don't have a lot of time, so I'm not giving you enough practice, but yeah, whatever I like, whatever we discuss, so during the week, so please have enough practice. So otherwise, everything like sounds like a story. So like, and you don't get the most of the next lectures. So so this is the prefix. So what this really means is, okay, we'll call with plus to it first of all, prefix of root. So and it says to print that. So the trees, so the prefix with plus will be called. So it has three statements. One is print, okay, so another one is prefix of left, right, so which is a, p of a, and then that has p, then the third statement, it has p of right, okay, so which is p of star, okay. In fact, so the compiler kind of like takes an expression tree here. You can see it as like this, right? So this is again an expression tree pretty much, right? Okay, so what happens? So it evaluates in this order, right? So it needs to execute p of plus, but before completing this, right, it has to evaluate its children, right? So just like for a plus b star c, so in order to complete this star, so we need to evaluate its children first, right? B and c first, right? So just like that, for any method, so to call it done, so you just get into it and execute those sequences from left to right or one by one, right? So you start with print, right? So which is printing plus, and then it needs to execute the p of a part. So of course it doesn't have any other children, so but yeah, it just calls p of a. So p of a has three statements. Okay, let me call the output here somewhere. So the output is here, like, okay, it prints plus, okay, and then it calls p of a. So it just gets into the p of a function, and then with p of a print root dot data, right? So that means it just prints a, okay, and then this is done. The p of a part is done. So now it needs to evaluate p of star. So p of star is called, okay, so obviously it prints star then, because that is, it just gets into this prefix function, and print is the first statement, print of root dot data, so which means star, right? So we just go with star, then it calls prefix of left and prefix of right, right? So which is p of what is left, b, and what is right, c, right? So now it needs to complete b, so it gets into this function with b, and now it will print b, okay, and okay, so there is a catch here. So the root dot left and root dot right are only called if it is not null. So I didn't keep that check, but please insert a check here that if root is null, okay, so let me undo this and write with some red ink or some other color, okay. If root is null, return, okay. So that means, in fact, for p of b, for p of c, for p of b, it prints the data which is b, and then it also tries to call the left node, so which is null here, so it doesn't have anything. So but yeah, it calls the null, so the p of null will get into it, and it sees that, okay, if it is null then return, and so that way it doesn't do anything. And similarly for the right happens. And now as part of p star, we got done with p of b, so now we need to evaluate p of c, right? So the function has to go to p of c. So now for p of c, it calls, it gets into it and it prints the data, so which is c, and then it calls the left, which is null, so it comes again into the prefix with null, which does nothing, and then it calls right, so which also does nothing, and it marks it done, and it goes back. So p of star part is done, so hence p of plus is also done, because all these three statements are done. So yeah, that's it. So that's the completion of this. So A plus B star C. So for that the prefix notation is this. Okay. Any doubts here? I know, like I kind of rushed through. So, but yeah, I don't have much time, and this is, I think, your part of your graduate course, and you will have a lot of examples on web. Okay. Next